Guys hear me? Okay. Good morning and thank you for joining my session, How to Scale MongoDB. Few words about me. My name is Igor. I come from Skopje, Republic of Macedonia. I have a master's degree in software engineering and initially started working as a web developer, then moved into the backend as a DBA with Oracle MS SQL databases, eventually started working with MySQL, and since 2012 I'm only working with MySQL and MongoDB. Since 2016 I'm lead database consultant for Pythian, and I have C100 DBA MongoDB certification. Brief overview, what we will discuss today. We will start with HA and how MongoDB achieves HA. Then we will talk about replica sets and different components, deployment topologies. Then we will move into scaling, vertical and horizontal, what is sharded cluster in MongoDB, the cluster components, shard keys, chunks, hashed and range-based sharding. We will see examples of how to choose shard key, and at the end we will have a Q&A session. So let's start with HA and why HA is important. We will mention this later in the talk, but HA stands for high availability, and it refers to systems that are durable and are likely to operate continuously without failure for a long time, compared to a single system that has HA should operate longer. Parallel with HA, there is this single point of failure, common thing that you can come into when discussing about HA, and single point of failure means that if it fails in a system, then the entire system stops. So as you can see from this diagram, both the database and the application are single point of failure, because if any of these breaks, the user will see the entire system stopped. So how do we improve the system? How do we add HA? Well, on the application side, it may be very trivial. We just add application servers in front of load balancer, and the balancer just sends the traffic with round robin. But how about on the database side? Do you have load balancer that will just send the traffic with round robin? Can you write to all of the nodes on the database? What is the primary? What is the node that accept writes? Where do you send the reads? So on the database side, it looks like more complicated. We have to direct all the writes to the primary, and we can read from the primary or any secondary, which is a replica of the primary. But that also involves additional software, so we have to know what is the current primary. What if the primary fails? How do we handle that? How it's on the application? Well, on the application side, if this server goes down, the load balancer will just notice and will send the traffic to the rest of the nodes. Is that the same on the database side? Just send the writes to any of these nodes? It doesn't look like that trivial. So with MongoDB, HA is achieved with replica sets, and a replica set is a group of MongoDB processes that maintain the same data set, which means If this is the primary server in a replica set, both secondaries have the exact same copy of the data. It provides redundancy and high availability. With replica sets, you also have increased read capacity, which means that now you not only send the reads to this node, but your application can send reads to the secondaries with eventual consistency. And in MongoDB, if this node goes down, the replica set will elect new primary from these two nodes. The failover is automatic, and the driver understands that. So you just connect your application with the driver to a replica set. The driver at any point of time knows what is the primary, what are the secondary nodes. If there is a failover, the driver handles that so that you don't have to change anything in the application. How does the replication concept work with MongoDB? All the writes from the application come to the primary node. Then all the changes are recorded into the primary node op log, which is called operations log. It's a kept collection that is idempotent. All the writes that come in that order are asynchronously replicated to the secondary nodes. The secondary nodes copy the primary op log to its own operations log and apply those operations log to the database that's on the secondary node. By doing that, secondary node can use a sync source other secondary because it is the same op log that comes from the primary. And that's by default with MongoDB 3.2 and above is true, which means that if this secondary wants to replicate from this secondary, it will offload from the primary so that these two can communicate. If this secondary lags for more than 90 seconds, or depends what is the exact threshold, this one will say you are lagging more than 90 seconds. I will continue replicating from the primary. Some configuration options about MongoDB replica sets. You can have 50 members in a MongoDB replica set. 7 of those can vote in elections. So when there is a failover, only 7 of those 50 members can vote. And there are options to have Arbiter node, priority 0 node, hidden node, and delayed node. Let's see what is Arbiter node in a replica set. Arbiter nodes does not hold copy of the data and are there just to participate in elections. So in typical HA setup, you would have 3 data nodes, and if any of the data nodes goes down, the two other data nodes will vote and they will decide what should be the new primary. However, it's possible that you have only 2 data nodes, and this node is only there to vote in elections. And when the primary goes down, the secondary will say, I have data, I want to be the primary. The arbiter will see the secondary that is alive, it's there, and the vote will go to the secondary. So this one will be the new primary. Another use case is where you want to have high availability across data centers, so that when this data center goes down, if you only have 2 data centers, these 2 cannot elect new primary because they don't have majority. The Arbiter is in the third data center, so when this data center entirely goes down, the Arbiter will be just right there to vote in elections, and you will always have a new primary. Priority 0 node is a secondary node. It's always a secondary, cannot become primary, and it cannot trigger elections. This node is visible to the driver, to the application, so that when you send read request to your replica set, the driver is able to see this node and read requests can go to this node. However, this node will never be elected as a primary because that's what it's set with priority 0. Hidden nodes are also always secondary nodes. It never becomes primary, and with difference from the priority 0 node, this node is not visible to the driver, so that the application does not see this node. If you send read requests from the application to the replica set, the driver will not see this node. And typically, you use hidden nodes for reporting, running ad hoc queries, or taking backups. Delayed node, similarly to hidden nodes and priority 0 nodes, it's always a secondary node. This node must be priority 0 because it has delay in the replication. So there is a configuration option where you can just say, delay this node by 1 hour, and this, by doing that, you will have previous copy of your database. This is useful, for example, if you want to take backups on a delay node, but also you can recover in case of a human error. If you run delete operation without any where clause and you figure out that you have deleted your data, this node can help you and you can recover. Any questions so far about HA? Okay. Now let's move into scaling. So we have high availability. We have our data set on a single server or multiple copies across a replica set. But when it's time to scale, with scaling, there is one variable that's bounded with every system, and that's the working set. Working set represents the amount of memory that a process needs in a given time interval. So if your working set fits into RAM, then you should be good. Your application will send and serve most of the requests from RAM. But if your working set outgrows the RAM memory on your server, then some of the requests that you send to the database will be served from disk, and those will probably be slower than working with your RAM. So when the working set outgrows the RAM memory, then it's probably time to scale. And scaling can be done in two different ways. You can scale vertically by adding more power, more hardware to the server, like more RAM, more CPU, more disk. And this might require downtime. If you want to stop the server, add more CPUs, more RAM. Sometimes in a virtual environments, this doesn't require downtime. You can scale vertically on the fly, but in some cases it does. And the other option for scaling is horizontal scaling. With horizontal scaling, you just add more machines and you partition the data across multiple machines. So that now, on a smaller server, you have only a portion of the data, and that portion will fit with the working set into RAM. With horizontal scaling, you want to parallelize the processing. However, this adds complexity, and it's not that trivial to implement. Vertical scaling, you have small server, the data set is 1 terabytes. What you do, you add larger server, still the data set might be 1 terabyte or it's the same. Have in mind that you not only have to scale this node, which is the primary, you have 3 nodes to scale. So if you think about the cost, you need to buy 3 larger instances, because you, at the same time while you're scaling, you also want to keep your high availability. The horizontal scaling, on the other hand, is you have your data on a server, it's 1 terabyte. Ideally, what you would like to do, split the data across multiple shards, so that now you don't have to scale vertically and buy larger instances, but on a smaller instances, you will have smaller data set that will, your working set will fit into RAM on these machines. The shard should be the exact same data when you split, like previously what you had in a replica set. Some notes about how much it costs vertical compared to horizontal scaling. Horizontal scaling is like a linear growing of the costs, but with vertical scaling, just to have the amount of CPUs that you can reach with horizontal scaling is more than 2 times expensive. And with vertical scaling, the costs grow almost exponentially. So let's move into scaling with MongoDB. As we discussed initially with MongoDB, we have our replica sets, and the replica set is what we call a shard. What we want to do, we have this shard. We want to split the data across multiple shards so that we can parallelize the processing, and all of the shards will have their working set fit into RAM. If you want to split additional, we can add new shard and then new shard. So we can add as many shards as we want. But this adds complexity. So now we have our data split across multiple shards. How the application will know where to pick data, whether it's from this shard or from the second shard? How do we route the queries? How do we know how to migrate data between the shards? So there are different components in a MongoDB sharded cluster that address all those issues. In a MongoDB sharded cluster, there are 3 components. The first component is the shards, or this is a replica set as we know it for high availability. The second component is config servers, and the config servers store the metadata for the cluster. So when we shard and we partition the data across multiple shards, config servers store all the information, what document exists on shard 1 and on shard 2 and across all of the shards. The application speaks to the cluster through a router or a mongos, and that's the third component, so that the application doesn't care what shard it should query. The application queries the mongos. Mongos gets the cluster metadata from the config servers, and it knows where to route the queries. So initially, when we set up a sharded cluster with MongoDB, and we enable sharding on a database, we shard a collection. After that, just adding additional shards is by running the command add shard, and we can add as many shards as we want. The database will partition all the data for us. We don't have to worry about what data to move to shard N or what data to move from shard 2 to shard 1 to balance. The database does that all for us. The first component of a sharded cluster are shards or replica sets. Every shard that you have in a cluster should be highly available. In a sharded cluster, each shard represents a unique copy of the data. If you lose a shard, you will lose that copy of the data, and it will be difficult to recover, almost impossible, if you lose that shard. Even if you want to restore from backups, you need to restore the entire cluster. So what we already discussed about high availability with MongoDB and replica sets and different deployment topologies, it's always good to keep your shards as replica sets for redundancy and high availability. In MongoDB, each database has its primary shard, and by default, when you create a database, the shard will assign any of the shards as the primary shard. By default, all the collections that you create will be on that shard. So at this time, sharding is not yet enabled. All the data will be in that single shard. Even if you might have 10 shards in your cluster, all the data will be on the primary shard. Sharding will only start when we enable sharding on that collection. If the database has multiple collections, or what we call in the relational databases tables, all those will be on the primary shard. So that's one important thing to notice, because sometimes we may see shards have more data compared to other shards, and that's because all the non-sharded collections in a cluster reside on the primary shard for the database. The config servers, as we mentioned, store the cluster metadata, and that's where the router gets the information and it knows to what shard to redirect the queries. Other than the metadata for the cluster, on the config servers is also the admin database, and that's where the users are stored. So when you authenticate to a cluster, the information is get from the config servers. Starting with MongoDB 3.4, the balancer is also a process that runs on the primary node of the config server. This section of the cluster is also a replica set, and it's replica set to have high availability. If this goes down, you will still be able to use the cluster. You will be able to send queries, even do writes, but the metadata will not change. So if you want to balance between the shards or add additional shard, that will not work because this will be down. So also important section must be highly available, and that's why it's created as a replica set. And the third part of the sharded cluster is MongoS. MongoS is only caching the metadata from the config servers, and it routes the queries to the shards. It doesn't have a persistent state. On each metadata changes, it updates the cache. So when you send a request from the driver to the MongoS, MongoS has the metadata in its cache, and it knows where to send your query. So we have our cluster. Now let's see what steps we need to take to shard a collection. If you are from the SQL world and not familiar with MongoDB, what we call as a collection in MongoDB, that's a table in the relational database. What we call as a document in MongoDB, in the relational database, that's like a record or a row. The first step, what we need to do is enable sharding on the database. Remember, each database has its primary shard. When we enable sharding on the database, then we can shard a collection or a table. And we do that by running the command shard collection, database.collection name, and we choose a shard key. So we'll see what is this shard key later, but by definition, it is an index key that must exist in every document in that collection. So if you have collection history and you store history for some users, user ID must exist in every document in that collection. If there is a single document that does not have this key, you cannot shard the collection by this key. There are two ways for sharding. One is range-based, and the other one is hash-based. With range-based, you shard the collection into ranges, starting from the min key up to the max key. You have ranges into the collection. With hash-based, you just use hashed key on that index, and the database will just distribute the documents across all the shards that you have in your database. So the range-based sharding is dividing your data into continuous ranges determined by the shard key values. What does that mean? For example, if you have shard key X, starting from the min key up to a certain range, you have one chunk, then a second range and a third, and so on, up to the max key. By using this kind of sharding, you have a query isolation, which means when your application queries and wants to find values between 25 and 30, it's more likely that the query will come to this shard, to this chunk, and you will end up querying only a single shard. With hash-based sharding, the database is using a hashed index. It has to be a single key index, and that's what's used to partition the data. By using hashed function, your data is more likely to be evenly distributed because all of these hashes will be split evenly across multiple chunks. But when you want to query for a certain range, for example, between 25 and 30, now you will have to query across all of the shards to find that data, because this is a hashed function, and you don't know whether value 25 is stored on this chunk or on this chunk. With a range sharding, it's more likely to have the values close to each other. With hashed, everything will be evenly distributed, but you will have to query all of the shards when it comes to querying in a range scan. So what's the ideal shard key when we want to shard our collection? The ideal shard key should have large cardinality, and that means it should have a lot of unique values. It should have a low shard key frequency. We will see later about cardinality and frequency. And now when it comes to range-based sharding or hash-based sharding, for range-based sharding, the shard key should not be a monotonically changing. Values like timestamps or underscore ID, those monotonically increase over time. For range-based sharding, that's not the ideal shard key. However, for hash-based sharding, monotonically changing shard keys are ideal, because in that case, the hashed function will just generate unique values and everything will be evenly distributed across the shard. And when we enable sharding with a shard key, everything is split into chunks. A chunk is a continuous range of shard key values that reside on a particular shard. It has inclusive lower and exclusive upper range of the shard key. By default, each chunk is 64 megabytes, but you can change it starting from 1 megabyte up to 1 gigabyte. So let's see what is the shard key cardinality. The ideal shard key should have high cardinality, and that's as many unique values as you may get. For example, if you have a shard key on X, if this key is from 1 to 1,000,000 and it has all those different values, it will be a good candidate for a shard key. But if you want to shard on this key and there are only 5 different values, all those 5 different values, when you want to split into chunks, you will end up into 5 chunks. Even if you want to add hundreds of shards, there will be only 5 chunks, and those can exist 1 chunk per shard. You will end up with only 5 shards, and that's all. You will not be able to split this data at all after the initial split, because your key has only 5 different values. Frequency. Even if you have a shard key that has many unique values, you need to be careful when deciding about the shard key to have low key frequency. If you decide to shard on a key that, for example, has values between 1 and 10,000, but there are multiple documents, hundreds of thousands of documents that have value 12. With range-based, all of these documents will end up in the same chunk. This chunk will be a giant chunk, and it will not be possible to split this chunk. So eventually, it will live on a single shard, and this shard will be hot. Every query that you want to find documents with value 12 will end up into this shard. And monotonically changing shard key. For a range-based sharding, this key is not good because over time, monotonically changing shard keys will end up all to the last shard in the latest chunk. If this is a range-based sharding, this will be the only shard that accepts writes. So your write workload will be how much writes this shard can take. That's what you defined for the entire cluster. After time, when this chunk will grow, it will be splitted, and the shard will distribute the chunks across the cluster. However, all your writes will end up into this last shard. So for a range-based sharding, this is not the ideal key. However, if you want to decide and do hash-based sharding, the hashes on these different values will be split across the multiple shards evenly. So let's see one example about choosing a shard key and what steps we need to take when we want to shard a collection. Before we even begin to shard a collection, we have to know what are the query patterns for the collection. What operations do we run, like find, delete, update. All the queries that we run, we have to understand, and what are the most common queries. Let's take example of collection users, and we want to query the data by username in that collection. In most of the cases where we have users, typically the username is the unique key. This allows high cardinality, low frequency, and it's not monotonically increasing. So in such case, we can consider username as our shard key. However, with MongoDB, if you have a unique key and you want to decide and shard the collection, you cannot add additional unique key in that collection. So if you have users and you want username to be the unique key and you want email, I've seen that, also to be unique, well, you cannot do that. You can only have a single unique key in a sharded collection. Another example is when you want to store history for some users in user history collection. User ID is typically with very high cardinality, and if your collection has low frequency for your users, which means a user can have at most 100 of documents into this collection, you can choose user ID as a single shard key. However, if you are querying the data by user ID and, for example, date created or some other key, and you have a high frequency for this user ID, the more ideal shard key will be the combination of these two. Another example is when you store information for write-intensive workloads, like capturing some views or log or anything that is very write-intensive, you typically have created on like timestamp, or you, in MongoDB you even have the underscore ID. If you just want to distribute this data across multiple shards and you only care about the write load, then you can shard this by using hashed sharding on the timestamp column. Some of the limitations that we already mentioned for shard keys. First, it must be ascending index key or compound key that exists in every document in the collection. If you want to shard by some key and there is at least one document that does not have that key, then your sharding will fail. You will not be even able to initiate sharding. The shard key cannot be a multi-key index, a text index, or geospatial index. It cannot exceed 512 bytes. Once you decide to shard, the shard key is immutable. You cannot change it. You cannot update the shard key. Update operations that affect a single document in a sharded cluster must include the shard key or the underscore ID. And as we mentioned, if you have a shard collection that has a unique index, you can decide and shard that collection on the unique index, or if you shard the collection, you will not be able to add additional unique index in that collection. So that's a limitation for sharding. So to summarize, when you have a replica set, always use odd number of voting members so that you are always highly available. Use hidden or delayed members in a replica set for dedicating functions like reporting, backups. If your data set fits into single server and you are aware how large is your working set, probably it will be better to keep unsharded environment than have the complexity of shards and documents and balancing and everything that comes with sharding. But your working set is one thing that you need to keep an eye on. When you have sharding enabled, always use your shards as a replica sets so that each shard is highly available. Once you decide sharding, the shard keys are immutable, and the max size of a shard key is 512 bytes. Shard keys must exist in every document in the collection. With range-based sharding, you may not distribute the data evenly, but with hash-based sharding, the data will be distributed randomly. And once you enable sharding, that adds a complexity for maintenance, like doing backups on a sharded cluster and doing upgrades, because you now have a bunch of servers. You need to do upgrades not for 2 or 3 servers in a replica set, but there will be hundreds of servers. Thank you, and any questions? All right, thank you.